Okay. So now we are on the second module of Internet of Things. So this is networking layer protocols actually. We were talking so far at the data link layer. Now we are at the next layer, which is networking layer. Now we come to 6th low pan. 6th low pan, the number 6 in the name indicates that it is designed for IPv6. Low stands for low power and PAN stands for personal area network. Alright, so IPv6 over low power wireless personal area network is 6th low pan. So broadcast, when you have broadcast, then all you need is the dispatch byte to be 50, that, and then a sequence number is added. So because what happens with the broadcast is you have to send it to your neighbor and they have to send to their neighbor and send to their neighbor. You don't want things to come back and then go again and again same place. So you put a sequence number, so that way you know that this sequence number I've already broadcasted, I'm not going to broadcast it again, and I'm not going to forward it again. Okay, so that there is no address required, nothing required, because it is going to everyone. Fragment header. Now there will be a lot of fragments. Why a lot of fragments? Why there would be a lot of fragments? Because IPv6 is so big and 15.4 is so little, there is no way you can send IPv6 into one frame at all. There is no way, right? And so there are a lot of fragments, and so the fragments have to be basically have a number. The dispatch byte is 1100. No, this is not the dispatch byte. This is the dispatch byte is 11. So dispatch byte is not shown here. But after the dispatch byte, the first 5 bits, if they are this value, then that is the first fragment. If it is this value, then it is second, third, fourth, fifth, sixth, nth fragment. Alright? So this 1 bit there indicates whether it is the first, whether it is not the first actually. 0 means first. Alright? And 1 means not the first. So once you have that, then you put the IP packet size, the datagram tag, and then payload. Or datagram tag and datagram offset. So let's just discuss those two. Full packet size in the first fragment, so it may not be here in the second one. Okay, and then you have datagram tag with sender and destination MAC addresses. Okay, so you have that, and then fragment offset. What is a fragment offset, or actually datagram offset? Fragment offset is when you break something in, you want to know which place this fragment belongs. So offset is just from the beginning of the packet to that point. Okay, that length in multiples of 8 bytes. So whatever the number of bytes before that fragment is, you divide that by 8. Whatever number you get, that is the number you put in the fragment datagram offset. Alright, why divide by 8? So that you just use 3 less bits. That's the only reason, because if you were to put all the numbers, then you will need 3 more bits. By dividing by 8, and then you just have to keep multiple of 8, which generally is already the case. And then the payload, as usual, we don't compress the payload. So what we have compressed so far is basically the headers and the fragments and things like that, right? So the first packet will have a different bit and the packet size and a tag, which is the number. Now, basically, this is the tag, which is 16-bit. It indicates that these are all the same packet. So they are somehow derived from the source and destination MAC address, because both of them could be very long. Either both of them could be 16-bit or could be 64-bit, or could be 48-bit, whatever. So the idea is that somehow you derive 16 bits, so this is like a packet number. And then all of them will have 1111 or 30, whatever number that is. And so you assemble all of them into one packet, one IPv6 packet. Alright? And the fragment offset helps you put the right place, this payload. This is very similar to the fragmentation in IP. If if they taught you fragmentation in IP, which they should have in 473, this is exactly how you do the fragment and the fragment offset. Now, so as you can see, notice here everything, basically every bit is very expensive, and so they are trying to reduce the number of bits as much as they can. So the next thing they need to reduce is the addresses. So before we reduce the address, let's understand the address format. So Ethernet had 48 bit, we already talked about, right? 48 bits are done as follows. First bit is called unicast, multicast. Top value is 0, bottom value is 1. If the first bit is 0, that means it is a Ethernet address is what? Unicast address. If the first bit is 1, it's a multicast address. And therefore, most of the devices that you have, Ethernet devices, they don't look at the whole address, they look at the first bit. If it is 1, then they just pick it up, regardless of what multicast address it is. Whether we are listening to that multicast or not is decided later. Okay? You just pick up a multicast, and then you look through the table of multicast addresses that you are looking at, and if it matches, you keep it, otherwise you throw it away. If the first bit is 0, then it's a unicast address, and right away you match all 47 bits left in a hardware, basically. So there is no table. Just you look up in a memory into it, what they call content at the SCAM, and then you pick it up. Okay, so the first bit is very important. It is universal or multicast. Second bit is actually unicast and multicast. Second bit is universal or local. Now this is really interesting because they use the word universal. You know what is the difference between global and universal? Does anybody know the difference between global and universal? How big is the globe and how big is the universe? Globe is so small. Universe is so big, right? So this is a universal address. Remember, if you go on the sun, it will be unique. And they are going on the sun right now, actually. So NASA has this solar network. So they will use universal unique address, right? So this is universal or local. So just like, basically at that time when we were designing Ethernet, 1978, there were two camps. One camp said that I want to address it by the building number and the room number and so on and so forth. And other people said, no, we want universally unique. Both camps won by having one bit which tells you which one it is. It turns out after that nobody has used your local yet, or it is not used much. So universal is one, finally one after so many years, but at that time it was not clear. So anyway, universal or local. But the only mistake they made was that they selected U equal to 0 and L equal to 1. If it is 1, then it is local. If it is universal, it is 0. And then 22-bit is the manufacturer, and that is called OUI. OUI, IOU or something like that, OUI is organizationally unique ID, simple thing for company ID. Okay, so if I look at your computer and find out your MAC address, I can tell you who made that chip. Whether Intel made it, AMD made it, Cisco made it, by looking at those 22 bits. There is a table on the internet where you can go and figure out the whole thing about the OUI. And then 24 bits are basically assigned by the company. 15.4 went further ahead and made it 64-bit, and they call it Extended Unique ID, EUI. Everything else is as before. First bit is universal, multicast, universal local, unicast, multicast, universal local. 22-bit of OUI, but then there are 40 bits instead of 24 bits, 16 more bits from the company. Alright, so this is what is called EUI. And actually, to be exact, it is called EUI 64. EUI 64 because it is 64-bit, and EUI because it is Extended Unique ID. Alright, now I just mentioned that this is a universal local, this was a mistake. Actually, it turns out, the broadcast address. What is the all broadcast address for Ethernet? All ones. So there, first bit is multicast, which is good. The second bit should be what? Should be 0 if it is to be universally unique multicast address. Right? But it turns out that broadcast address would be classified as local by that bit interpretation. But that's an exception. So they made an exception that if it is all ones, it is unique, globally unique broadcast. Period. Done. So it's not a local address, but it's one, but it's universal. Anyway, so the reason I have to bring that up is because this is IETF is trying to fix that part. So the local one was incorrectly assigned by the original people. So now IETF wants to relabel these bits, and they want to call it 1 if it is local, 0 if it is universal, because most of the time it will be 0. Nobody uses local addresses. If there are zeros, we can get rid of them very fast. Right? So when you're thinking about compression, when you're thinking about smaller things, it's better to have zeros than ones. If nobody is using that local addresses, so we call them 1. But all broadcast addresses are 1. Okay, so that's the mistake. Now the thing is, IETF 4291 changed the meaning so that L equal to 0 means local, and the second bit is called universal bit. Okay, you name it universal. You make the bits are called by their whatever the 1 means. So this is a multicast bit. This is now a universal bit if you follow 4291. So if you write an address in U-bit formatted UI64, EUI64, then you will take EUI64, flip the second bit, and that would be called U-bit formatted EUI64. That would be called RFC 4291 format. Having done that, now we can take these 64 bits and put them into this format. Now, how can read this double colon? What does that mean? So this is IPv6 notation for addressing. Is that since the addresses are so big and most of it is 0 anyway, so they don't want to write zeros, so they write 2 colons. 2 colons means fill up as many zeros as you need. So here FE0 is 1 byte, 2 bytes. Right? And this one is 64 bits, 8 bytes. Total we have 10 bytes and we need 16. So we put 6 bytes of zeros there. If you were to expand this, you will write, so now we are writing 2 bytes at a time, right? So you write FE80 colon 00. Okay, I mean you can either write 8 zeros if you're writing in binary, or you could write 2 zeros if you're writing in hex. So 00 colon 00 colon 00 colon, well actually 4 zeros will make 2 bytes, right, because each thing is a nibble. So you write 4 zeros colon 4 zeros colon 4 zeros colon, you write it 3 times, that will make it 6 bytes. And that address is called link local. Again, this is IPv6 concept, and we teach, I taught all this in 1991. Believe it or not, I taught it not 91. I taught it in 1994 when I taught my first IPv6 class, and I have taught it in every every 473. But a lot of people are coming up here without any knowledge of IPv6, which is really pathetic. But link local means that this address is good only on the link inside the house. Just like 16-bit addresses, link local addresses are inside the house, and so you don't need DSCP. You can make up your own address and be in business right away. Alright, this is called auto configuration in IPv6. So any device who knows its UI, which is built into the hardware anyway, can make its IPv6 address like this. It will just put FE80 in front of it, put 6 zeros, and then put its 64-bit address. Now it says this is my IP address, and it can start talking to everybody. The only difficulty is that it cannot talk to anybody outside, because this is link local. This is not global address. Somebody else might have the same address. Actually, they will not have it because they will not have the same EUI64. But link local addresses are not supposed to, they are just like private addresses. So you cannot get out. If you want to get out, you need to get a global address, and then so for that you do have to go to somebody and find out what is my network prefix. And the network prefix actually in IPv6 is the first 8 bytes, 64-bit. If you get that and then you put whatever you want to put after those 64-bit, that would be globally unique because that network is only here, nowhere else in the world. So this is link local address. So you get a link local address from your EUI 64-bit address. Again, one more time, how do you get it? First thing you do is you flip a bit. Which bit? The second bit. And once you flip that bit, then you add 6 zeros in the front, and then you add FE80 in the front. I said them say 80. FE80. Because it's all hex. Alright. So I gave an example here. Suppose your link local address, so suppose your EI64 address is 40, and I'm kind of misusing this double colon here because EUI doesn't use double colons. But since it is so long, I don't want to write too many zeros. So 40 is, sorry, not 40, 40 is this 40 colon colon 01. If I U-bit format it, I will flip the second bit. So I will get 0 colon colon 1. Now how many things I am skipping here? Tell me. How many zeros am I skipping? For 64-bit, how many bytes do I need? 8. How many do I have? 2 bytes. 4 nibbles, 2 bytes. So I am skipping 6 zeros in the middle. Imagine that you have all those 6 zeros in the middle. This is your U-bit format addresses, and then you make it your link local address by putting 6 more zeros in the front, and then FE, F and E, 8 and 0. So now you understand how you can get an IPv6 address without going to a DHCP server. You see, on IPv4, you cannot do this. You cannot just make up your address and start talking, because somebody else has already decided what the network is and what the service mask is and all that. So you have to get it from somebody. So you have to go to DHCP. And this was one of the features of IPv6, which was advertised right at the beginning, that this is a good thing that we just plug and play. All right. IEEE 15.4 allows you to have 16-bit sort addresses, and each PAN has a 16-bit PAN ID. Okay, so you have 32-bit 64-bit address yourself, and you are part of a home or a network that has 16-bit address itself. Okay, so you don't use 64-bit, but you're going to use 16-bit of yourself and then 16-bit of the home address, PAN ID. 1 bit of the sort address and the PAN ID is unicast multicast. Now PAN ID is very similar to the other addresses we have seen. The first bit will indicate it is unicast or multicast. Second bit will indicate whether it is universal or local. And if you put all ones, that means broadcast. That means I want to broadcast it to all the networks that I can reach. All the PANs, not just, okay. If you put that PAN ID fixed, not all ones, but you put all ones for the host part, then you want to broadcast to all the hosts of this PAN. So broadcast is of 2 types, right? In PAN broadcast, out of PAN broadcast. In PAN broadcast, you have a fixed PAN ID, but the host address, destination address is all ones. Out of PAN is the PAN itself is 1111111. Now you will form an IPv6 address by putting FE80 and putting lot more colons, lot more zeros, then PAN ID and sort address. If you don't know the PAN ID, just use zeros, because we love zeros. So anyway, put zeros, and then at the end you have a sort address. Second bit of the PAN ID will always be 0, since it is always local. And the second most significant bit. Now here you think, when I was reading about this, a lot of people are confused about this bit sequence. And I wrote a whole book on FDDI, which was the 100 megabit Ethernet. So I know exactly. So basically, how do you count the bits? A lot of people put 6th bit, and they're counting from the right. You don't count from the right, you count from the left. So you always have to count from the most significant bit. Okay, so when we say 0th bit, we mean the most significant bit. When we say first bit, that is the second, and so on and so forth. So 0, 1, 2, all the way to 31, right? So second most significant, here I don't mean number 2, it is second most is basically, if you were to level from 0, that will be bit number 1. So second most significant bit should always be 0, because that is what indicates local or universal. It's really strange. I was just thinking about this global versus universal. IP doesn't use the word universal. IP uses the word global. Okay, Ethernet uses universal. So Ethernet is, and I think basically because IP was designed first, they didn't think of going universally. So they were thinking globally. But Ethernet came later and they thought universally, right? So that's why. But they are they are basically same meaning right now. It doesn't really make a difference whether it's global or universal. But it's just interesting to know that the words are different. All right. So now you know two ways to make the IPv6 addresses. One is if you know the complete 64-bit, then you do that. If you use 16-bit sort addresses, then you know how to do that too. Right? So either from your pet name, which is your home name, 16-bit address, you can make the whole address, or from your unique name, full name, you can make the whole address.